Imagine you were trying to find how far a ball will roll after being hit by an initial ball, and you know the mass of the tennis ball, you know the velocity and all the other basic necessities to fill out the equation, but you come to find that there's little to no information about rolling friction of a tennis ball on the surface that you're testing on, let alone any surface at all. So today we're going to use equations and apply them to our experiment from Wabash College in Physics 109 to apply it to a model that we have created of a ball on a ramp at a certain height colliding into a second ball from a certain distance away to measure how far the distance of the ball will roll on multiple trials.
Today we're doing an experiment that has to do with rolling friction. So in order to do this experiment and calculate the rolling friction, we needed to take some measurements. Some of these include height and the average distance traveled of the second ball after it is made contact with the first ball. In our actual experiment, we did 5 trials. This was to make sure we could get good average values while also calculating uncertainty. And the kind of first value we measured was the height of the ball before we're going to drop it for the collision, and that was about 11 centimeters or 0.11 meters. Then we did our 5 trials measuring the distance the second ball goes after contact. Let's straighten that out. And then make sure our balls have a head-on collision. So here's an example. All right, so the second ball is gonna start at the 10 centimeter mark or 0.1 meters, and we're gonna go ahead and drop this. And the ball rolled to about 77, 76 centimeters before stopping. That's about a gain of 66 to 67 centimeters or 0.66, 0.67 meters.
So here we're finding the coefficient of rolling friction, and to do this, we have to remember that this is an energy equation. So for potential energy, it is mass times gravity times height, and for the kinetic energy, it is 1/2 mass times velocity squared plus 1/2 inertia times velocity, or angular velocity squared. And by assuming that this is a perfectly elastic collision, we can assume that it equals 1 and just this cancels out in itself, and we don't have to worry about that. But this also equals work, and we know that work equals force times distance. Now the force of friction in this situation equals mu times mass times gravity, and we're trying to find mu. So by doing this, we come up with the equation where mass times gravity times height equals mu times mass times gravity times distance by simply plugging this into this equation right here. Now we can cancel out mass and gravity because the mass, they also cancel out, but for both balls, they are the same amount of weight or grams in mass. So by doing that, we then come with the final equation, which is mu equals height times distance. Now we found height, which we have already shown, which is 0.11 meters. And also by taking our average, which we had 5 trials like we already stated, and our average meters that the second ball rolled was exactly 0.70 meters with the uncertainty of 0.07 meters. So then we can finally plug in the equation for our calculation of coefficient of rolling friction as 0.11 meters, which again is the height, divided by 0.70 meters, which is the average distance traveled, to get our final calculation of coefficient of rolling friction as 0.16. So before the experiment started, we as a team came up with a prediction. The prediction of what we thought the coefficient of rolling friction was of a tennis ball on a tile surface. We came up with an estimate of it being about 0.1, maybe a little less than 0.1. We came up with this by some research of what the sliding friction of a tennis ball is on a tile surface. And the numbers that we had found in the research that gave us was around 0.5, maybe 0.6. Now, we had come up with the estimate of 0.1 by knowing that the sliding friction is usually significantly higher than the rolling friction itself. Now, we did not know any estimate because there is not very much numbers or calculations of what the actual rolling friction of a tennis ball on a sliding or on a tile surface is. Now, of course, we know now that based on our measurements and our calculations that it is around 0.16. And that is a little higher than what we predicted, but still in the ballpark, not quite that too extreme. Now, this could be of one of many things. One is that we assumed that it was a perfectly elastic collision. That may not be the case, which kind of skewed our data a little bit. Also, by looking at other variables or other calculations, the rolling friction of a tire on loose sand is about 0.2 to 0.4. So by our estimate, our calculations, a tennis ball on a tile surface is just below that. And it being a fuzzy surface, it could very well be reasonable.